Okay, yeah, please, Ilka, whenever you're ready. Thank you.
Okay, good. So wonderful. So welcome to this first part of a double talk on very basic things about how and why torsion pops up in differential geometry, why we should care about it, part one, and hopefully why it is interesting. So at the end of these two talks, I hope you will share this point of view that torsion is a useful tool. Okay, so I have a very brief outline here, which first introduces the basic notions and concepts about metric connections with torsion and tries to give a first answer to the question, why should we have a look at torsion? We say something about the Cartan types of metric connections and what role torsion plays in this context. Then we shift a little bit the point of view, and then we have a look at holonomy as being a key technique in modern differential geometry. And so connections with torsion bring a new aspect into this approach. Then we do the Ambrosinger Homogeneity Theorem, and I call it like that because there are many theorems, or several ones, which go by the name Ambrosinger Theorem, and we shall encounter at least two of them. And then as a nice example, which ties many of these things together, I will speak about the almost complex structure on S6, the relation to nearly scalar manifolds, and a few modern aspects of the theory of nearly scalar manifolds and how all this ties up. Okay, so this is where we want to go. And as you can see, I have here my pen. So any questions you may have, I will just scribble on the screen as it happens, right? And you just, since it seems that we're not many people, you just interrupt me. You just do it, because I cannot see the chat, but I can hear you. Okay. So here we have a picture of the local hero of the topic, which is Élie Cartan. And Élie Cartan, in one of his papers on connections, actually, he did not focus so much on the Levi-Civita connection, but he issued this kind of program or principle that given a manifold embedded in a affine or projective or conformal space, one should attribute to this manifold the affine or projective or conformal connection that reflects in the simplest possible way the relations of this manifold with the ambient space. So we're not going to do projective or conformal geometry, but the idea is that to each kind of geometry, there should be, or there is, a notion of compatible or adapted connections in a naive sense, right? And what we would like to do is to find out which they are and try to extract information. And the original citation is on the bottom of the page. Okay. So for the anecdote, I own the complete works of Élie Cartan. And so whenever, you want to do some reading and peek over the shoulders of the giants, I take one of these volumes and I try to understand what Élie Cartan was writing. And the problem is not the French, the problem is the math. But that's fun. Yeah, going back to the original sources is something I like to do. Okay, so that's where I took the quote from. And now, very basic, let's step back to the elementary course in differential geometry, actually submanifold theory, right? We know that even if we have two vector fields which are tangential to a manifold, if we take the directional derivative, in general, this is not going to be tangential to the manifold. And so looking at some tangent space, TPM of my manifold, one brutal but efficient way of getting a connection is to just force this to lie in the tangent space. That is, we project down the directional derivative as we learned it in calculus to the tangent space. And this projection turns out to have all the properties that we would like to have, and therefore it is a connection. This connection is indeed the Levi-Civita connection. And now when doing so, of course, it only works for submanifolds. So I consider my induced metric. In particular, there is a metric Okay, and this projection, orthogonal projection, turns out to be compatible with the metric in a good sense, and it turns out to be a so-called torsion-free connection. Now, the definition of torsion we do later, but in any event, this is a way to get a connection quickly. Nevertheless, it is well known, I think quite a while, that connections with torsion pop up in a natural way. And the first definition of torsion was given indeed by Cartan. And an example you may have encountered early in studies is in electrodynamics. So in theoretical electrodynamics, there comes a moment where a gauge potential, which is just a one form, right, is introduced, and people just tell you you need to replace your normal partial derivatives by something new. Namely, you take the first part as usually, and then you add something which depends on the gauge potential, which is you evaluate the one form on the vector field u, and this is a function, then you multiply it with the vector field v, and then you have some constants to add just to first to ring the bell in your mind what kind of connection I might be speaking of, and to show that you know what the physicists are doing. So the formula one encounters in all books on electrodynamics is written in index notation. Lambda mu equals derivative del mu plus 1 IE over h bar a mu, right? A mu just being the components of the one form, which in this sense, then I would just identify with the dual vector field. Okay, I studied physics. I found this very disappointing when I saw it first in a physics class. Motivation, zero, none, just do it, right? By now I understand that giving a motivation is actually not that easy, and that probably most people just take it for granted and do not even think about motivations anymore at this place. Let's look at the second easy but instructive example. We take free space and we define a connection, so a derivation rule, by taking again the normal directional derivative in R3. And then since we are in R3, we have the vector cross product. And so we can take the cross product of the vector field u and v and just add any multiple we like of this cross product. This is again a vector field. And then the funny thing is that just as it's a nice exercise for a calculus class actually, to check that this would satisfy a product rule and all the things you would expect, except that for commuting vector fields, you don't get, you get a commutator vector field, no, for commuting vector fields, so vector fields, which would be just derivatives in coordinate directions, you do not get that they commute as you would expect them to commute. But except for that, everything else works fine. Now, this example here is actually what Cartan did. And so this word torsion, it really comes from Élie Cartan imagining that space has some kind of internal angular momentum. And so he was actually thinking that space is tordu. For those speaking French, tordu means well, it has some kind of twist, a spin, right? So in each point of space, you have an internal spin, which somehow gives you some twist. And this twist he called torsion. Okay. This example also shows that he had actually a physical motivation behind, right? The concepts of space and time as we know them were not yet fixed at the time. And so introducing torsion was seen as a way to introduce some new internal physics for describing symmetries. Now, the fact that we're going to explain in a little bit more detail in a few slides is the following. namely that there are basically 3 types of torsion, and then of course you can take linear combinations. And these 3 types of torsion means they can be basically vectorial, meaning coming from a vector field. So that would be this situation, because vector field and one form just means the same here. Then there can be skew symmetric, which would be something like this, right? This is anti-symmetric in U and V, which is not the case in electrodynamics. And then there comes something else about which I will say almost nothing, for reasons which become obvious when we see it in detail. Okay, so and any linear combinations of these are accessible, of course. Good. Didn't lose anybody so far? Good. Okay, so why torsion? Well, so the first was motivation from general relativity. So Cartan, around 1929, 1930, had this idea of viewing torsion as some intrinsic angular momentum of space. And he derived a possible set of gravitational field equations. Right? If we look back, we have Einstein, 1915. Now, it took a few years to see that for what it covered, this theory was right. But what was the ultimate goal, of course, was to incorporate quantum mechanics into this new theory of general relativity. And so there were some tries. Okay, so general relativity. So Cartan described just from mathematical principles what alternative gravitational field equations one could have, but postulated in this context that the main restriction of general relativity, namely that the energy momentum tensor be a divergence-free tensor, should still hold. And then it turned out quickly that with this theory, there was nothing to be gained. It was just a more complicated approach, which would not reproduce the Einstein equations in the right way. And so this approach was quickly given up. Okay. However, the idea had a revival, and this revival was after the Second World War, and which is now known by the name of Einstein-Cartan theory, which is, by the way, a direction in general relativity where there's still work done. So the idea here was to change the Lagrangian from which you deduce your field equations. So the approach was not only to take the Einstein-Hilbert functional of general relativity and to change or to vary the scalar curvature, but to take an additional Lagrangian, which would generate the energy momentum and the spin tensors. And if you do that, you allow more freedom because the connections will turn out to be of any possible torsion. And in general, they will not be compatible with the metric. So these are not metric connections. And then you get a workable theory. So this is still done. Okay, good. Now, theoretical physicists know, of course, about all these things, right? Because this is part of their general education. And so, when in the early 80s, superstring theory came along, it was a rather natural thing to do to incorporate these notions of differential geometry, which were already existing, into these new models. So in classical Yang-Mills theory, curvature, so the mathematical concept of curvature, is interpreted on the physics side as a field strength, right? Whereas in superstring theories, torsion will play the role of the field strengths, and one will interpret field strengths as being higher order torsions. Okay. However, plus some extra differential equations, which I'm not gonna speak about. So with that approach, now things get more complicated, but in any event, curvature somehow loses its status as being the fundamental quantity and moves over to torsion, or at least to the combination of curvature and torsion at the same time. We will see later, if we look at the degrees of freedom, then actually we will see that torsion is an object which is, algebraically speaking, of less complexity than curvature, which might be one of the reasons why it's good to consider. Okay. Finally, we're not only there to help the physicists do their job, but we do also want to learn something about our own topic. So let me emphasize that connections with torsion, also certain super interesting applications happen in physics, is also of big importance internally inside differential geometry. Because this concept of having connections adapted to the geometry is a useful concept in geometry as well. And in particular, this works very well for what will be called in a few slides non-integrable geometries. So by non-integrable, for example, I would denote a manifold which is Hermitian but non-Kähler, or a contact manifold, okay, or a non-integrable G2 manifold and things like that. So a class of manifolds which are not as well behaved as we know it, for example, from the Kähler case. Okay, good. So this is the first moment for questions. That's why I put some empty pages inside here. Questions, comments, anything about this physics?
So I guess this the three form in this like Einstein-Cartan theory is sort of, it's fundamentally different, I guess, from the string theoretic appearance. Is this right? They're not really meant to be the same thing.
This is right. And in fact, it gives you an example of some very fruitful idea. So whenever I teach mathematical physics, I try to convince my students that they should always separate two things, namely the mathematical modeling, the mathematical objects from their physical interpretation. Because just as torsion shows, right, torsion in differential geometry is always the same, it's torsion. But in Einstein-Cartan theory, this torsion was interpreted as internal spin of space, right? Whereas in superstring theory, the physical interpretation of torsion is a completely different one. It is basically some kind of field strength. Right? And then the role of torsion in the equations changes rapidly. So the results and theorems about connections with torsion are one thing, the physical interpretation of something completely different. I can give you another different, but in the same flavor example of that. So I will not speak about spinors and spin geometry, but a spinor, you know, in old quantum mechanics, a spinor would just describe an electron. This is what you do with the Dirac equation, as Dirac invented it. Whereas in modern supersymmetric theories, the spinor would implement a supersymmetric transformation. Right? So yes, the role of mathematical objects changes all along. Right? And sometimes I give the following picture. You know, in classical physics, you have a particle which moves along a curve, gamma, and then the potential is a one form, and then a field would be the integral of a one form over the curve. Okay, but now in supersymmetric theories and in superstring theories in particular, the fundamental objects are not curves anymore, but let's say some two-dimensional surface. This would be a piece of surface, okay? And then you want to integrate over a surface, but then it means that your potential should be a two-form. Okay. And if it's a two-form, so that you can build the integral, then here the field afterwards is dA. So if A is a one form, F is a two form, whereas if I now take the derivative of dA here, this is going to be a free form. But a free form is not a curvature. So that's in a nutshell, why torsions all of a sudden starts to play a role which was taken by curvature before. Right? Just because all objects, fundamental objects, have now higher dimensions. You have this fundamental string, right, which is the replacement for my point particle concept, which then moves along surfaces or vanes or whatever you want to call them. This gives at least the idea why one needs to shift dimensions. Any other comments or questions I can speak about? Okay, good. So if something occurs, you let me know. Good. So what is the setup we're going to use? We start with a Riemannian manifold, MG. And we take a metric connection, just meaning, of course, nabla G is 0. And we denote for reference by nabla G the Levi-Civita connection. Right. Then torsion is usually viewed as a 2-1 tensor. And this 2-1 tensor is given by nabla xy minus nabla yx minus commutator xy. Now, via the metric, we can build a free zero tensor out of it, which is just given by txyz is scalar product of txy comma z. So for me, torsion is really a free zero tensor, and I will work with the two pictures as needed. The first observation is, now any connection, of course, is not determined by its torsion, but if it's metric, then it is, which one checks quickly by the space of tensors describing them. Okay, again, more details to follow. We call it a skew torsion or skew symmetric torsion if this torsion is a free form, which does make sense here, right? Because I have three arguments in my torsion, x, y, z. Now it's clear that T is antisymmetric with respect to x and y, because this is inherited by the 2-1 torsion tensor I started with. But a priori, the torsion tensor does not have any particular reason to be antisymmetric with respect to z, because that enters the picture just by contracting with the metric. But of course, algebraically, it's possible that it is antisymmetric, and then T is a free form. And in particular, we see that the notion of T being a free form or skew symmetric torsion only makes sense with respect to a given Riemannian metric. If this is the case, then the connection may be expressed in the following way. Nabla xy is equal to Levi-Civita connection, just as my reference connection, plus, and then one checks that the right number normalization factor is 1/2 txy, where this is one form and I just dualize as needed. Okay. In particular, we see vanishing torsion will just reduce my connection to the Levi-Civita connection. But the case of vanishing torsion is sort of this should be viewed as the degenerate. Okay, we will see what that means in examples. So this torsion is in some sense going to play the role of some kind of obstruction, right? And it quantifies this obstruction. And so the interesting thing is when there is an obstruction, right? Okay. Good. Further questions? Something? Good. Okay. So differential geometry is a theory which basically lives from examples. So I'm a big fan of examples. A good example tells you more than 100 boring theorems. So here comes a key example, actually, compact Lie groups. Okay, so we start with a compact Lie group, G, and denote by script G its tangent space. Okay, now do you notice that the speaker comes from Germany if he knows or she knows how to draw these factorial letters? Okay, so this is my G. I always like to impress my students and tell them that they should learn how to write German letters when they want to do Lie groups. So a metric G. Now we don't take any metric, but in fact we take a bi-invariant metric. So my metric is called bi-invariant if left and right translations are both isometries. And isometries, this can be catched in one equation, namely the scalar product has the property that the commutator, we have here, I need some assumptions. So for all in the Lie algebra. Okay, so I take the commutator of two vector fields Vx, and then the scalar product with y. This should plus the scalar product of x itself with Vy should be 0. Okay, which of course we can just rewrite in terms of the adjoint action, namely G of at V on x comma y is anti-symmetric. Okay, and anti-symmetric just means an element of the orthogonal Lie algebra. Okay, so let's remember this equation. And then it's easy to prove that the Levi-Civita connection is given by 1/2 the bracket for any vector fields. Okay. Now let's make the ansatz that the torsion is proportional to the commutator. This is not totally stupid, because I mean the torsion is a bilinear object which is skew symmetric and takes two vector fields and turns them into another vector field. And if you're just given any abstract Lie algebra, there are not many maps with that property which come to your mind. The commutator is the obvious one, and not only that, it's also the only one which you have on a given abstract Lie algebra. So this is the ansatz that we choose. So we pick a parameter s in the real numbers and define nabla sxy as being s times the commutator. Okay, then you plug in the formula for the torsion, and you realize that for this connection, the torsion is given by 2s minus 1 times the commutator. And now happens the nice thing, namely, we ask ourselves, when is this element a free form? And you see, well, this is going to be a free form if and only if the metric satisfies equation star. So being a free form or being a skew torsion element tensor is equivalent for the metric to be invariant. Right? And so since we started with a B-invariant metric, we have that property. And then you go on, compute the connection of this curvature, the curvature of this connection, sorry. Which is going to depend on the parameter s, of course, and the curvature transformation turns out to be a multiple of the double commutator Z with xy, and the factor in front is S times 1 minus S. Now we have three special cases. The first special case here, when we look at the torsion, is that when is this equal to 0? Well, if and only if S equals 1/2. Now this is fine because we cover the result that the torsion vanishes for the Levi-Civita connection, and the Levi-Civita connection, as we had seen, corresponds to S equals 1/2. So this is compatible. And now this maybe surprising thing is that for the Levi-Civita connection, S equals 1/2, the curvature is just 1/4 the double commutator. And there are two values, namely S equals 0 and 1, for which the curvature vanishes. Right? So for this connection is going to be flat for the values of S being 0 and 1. And this is a very remarkable and rather rare property. So these two flat connections were already identified by Cartan and Schouten, 1926, and they call them the plus-minus connection. Plus-minus because if you write it down and you see it's plus, plus 1 or minus the commutator, and it becomes more symmetric. So the parameter is just chosen in a symmetric way. Okay. Now, this case of a compact Lie group is in some way the flat case. Not totally, but almost. If you think of the Levi-Civita connection, right? For the Levi-Civita connection, the flat case is just Rn, right? If the Levi-Civita connection has no curvature, then you prove that you are isometric to a piece of flat Rn. Whereas now, in this skew torsion case, we see that the flat situation does not correspond to flat Rn, but it would correspond to Lie groups. And this is a picture we would like to develop in forthcoming parts of the talk. Okay, but for the moment, we observe it, not that it would be in any way deep or difficult to prove, but it's remarkable nevertheless. Okay. Now let's describe the different types of metric connections as Cartan did. Now, first, let me explain more in detail the relation to torsion. So we start with an oriented Riemannian manifold, nabla any connection. Then any connection can, of course, be written as the Levi-Civita connection plus some difference tensor, A. Then you just spell out what it means for the connection to be metric. And metric is a condition to be imposed on this difference term A. And in fact, if you check, then you see that A has to be antisymmetric in the following sense. So if I view it as a free zero tensor, A has to be an element in the tensor product of Rn with two forms, right? Because it has arbitrary symmetry in the last argument, and it has two arguments where it anti-commutes. So here the anti-symmetry is here, right? If I swap y and z, then I get 0. Okay. So algebraically, this is the space of difference tensors for metric connections. And now if I have a metric connection, then I have an explicit formula which links the difference tensor to the torsion tensor. Just in the following sense, well, the first equation, the second actually, is very easy to compute. If you have A, then you sit down, spell out the definition of torsion, and you see that the torsion is going to be this combination. not totally trivial, but not difficult as well, is to express A directly through T, which is the expression. And so you see that algebraically, the space of difference tensors and the space of torsion tensors are just the same. It's this tensor product of Rn times two forms. And as a vector space, or section of tensor bundle, if we don't take the local picture, the dimension of this space is n squared times n minus 1 over 2. In particular, for example, for the case of surfaces, okay, when n equals 2, the space of tensors where you have the freedom to choose your difference tensor or equivalently your torsion is 2 times 2 times 1 over 2, so the dimension is 2. Okay, and then in higher in dimension 1, the question isn't interesting, and in dimension 3, then you start getting something. Okay, and now maybe some of you see what Cartan did. He takes this space of torsion tensors or of difference tensors, doesn't matter. Now you have a natural action of SON on that space, because I have SON acting on Rn in the usual way. In the standard representation, I have SON acting on two forms. So I have the group SON acting on my space of tensors, and he just decomposes this as a representation. So decompose the space under the action of SON. And then you get the following result. Under the action of SON, this representation is not irreducible, but rather it decomposes into three parts. One is isomorphic to Rn, so the standard representation of SON on Rn, plus one term which is irreducible and isomorphic to the space of free forms on Rn, plus something else. So we're slowly getting there. Okay, so we see that from the point of view of the structure group SON of our Riemannian-oriented manifold, the space of torsion tensors decomposes in a natural way in these three summations. Now let's have a short look at the special case when n equals 2. Then we had computed that the dimension of the space of tensors is actually 2, and moreover, it's irreducible. So the assumption n larger equal to 3 here just ensures that the two parts here are non-empty, right? Whereas the case of n equals 2 is somehow degenerate or special, because then in n equals 2, you only have the first part and the two others vanish. Okay, now I go to the next slide because it's empty, so I have to have some space. So what can we say about this T prime? Okay, remember that my space of tensors was just isomorphic to Rn times two forms, and this decomposed into Rn plus three forms plus T prime. Now, here you have these two representations. They are defined by a highest weight, okay, and the theorem. So if it's lambda and mu, the theorem of the highest weight tells you that inside the tensor product of two representations with highest weights, lambda and mu, you will always find a copy of the representation with highest weight, lambda plus mu. And this is actually exactly this T prime. So in fact, T prime is the largest part of this decomposition. The only, from the point of view of representation theory, there's nothing to be said. The trouble is that in general, T prime has no geometric interpretation. It's just some representation of the group, whereas the two other pieces can be identified with tensorial representations. That's actually the big difference. So for these other two parts, we have a geometric way to deal with them and to identify them with normal tensors, whereas with T prime, we don't know. Okay, but since this is of the largest part, the open question is, and there have been a few first papers on that, but not many, is what can be said about this last part? What are geometries where it plays a role? When is this of interest? And it's always the same. You have more nice projects than you have students. Okay, so it's just that we didn't have time so far to do it. But for for master thesis or something like that, it's perfect because you have very elementary questions you can deal with, and something is going to come out of it. Maybe not the Fields Medal, but something. So this is actually nice. Okay. Now I will give you the concrete realization of the two other cases, namely the vector and the freeform situation. First, let's look at A being a freeform. Then these are exactly our connections with skew torsion. We had guessed it. And then nabla xy is given by Levi Civita plus 1/2 the torsion. Here's a first geometric interpretation which makes this class more interesting than the others. We have to follow, you can ask yourself the following lemma or the following question, namely, now then when you add torsion, what are the geodesics of this new connection? So in general, you will change them. And the lemma is that nabla is a metric connection preserving the Riemannian geodesics if and only if the torsion T lies totally in lambda free. So only in the torsion has only a freeform component. Right? In this case, 2A equals T, which was obvious from the formula we had before, and nabla killing vector fields coincide with Riemannian killing vector fields. So generators of isometries are still interesting vector fields. And from a physics point of view, I interpret this result as saying, I don't change the dynamics, right? Because test particles measure dynamics, and this is done using the connection. And so here, just by measuring geodesics, I will never be able to detect torsion if I view it as a physical experiment, right? Because the geodesics are the same. Well, as soon as my geodesics deviate from what they should be in the Riemannian case, I have proof of a torsion, which is not of skew symmetric part. Or differently, if I want to gain freedom in my connection, but I know that the geodesics are extremely well measured and just correspond to the Riemannian case, then I have to opt skew symmetric torsion because the others are going to change something, right? So this explains one reason why these are so interesting in physics. And there is, from a mathematical point of view, also the obvious consequence of this theorem, which tells us that the connection with a connection with skew torsion is going to be a complete connection, if and only if the Levi-Civita is complete. And so I just apply Hopf-Renal theorem, which is not true in the other situations, right? Geodesic completeness becomes a very tough question for the two other parts. Okay, let's have a look at this vectorial case because the number of freedoms is small. So these are called connections with vectorial torsion. And if you have a vector field, then explicitly this connection is given by the formula nabla xy, Levi-Civita, minus scalar product xy times v plus scalar product yv times x. And in particular, because of the observation above, any metric connection on a surface has to be of this type, right, of factorial torsion, which is something nice. And there are some nice results on the theory of surfaces using factorial torsion. Okay, now it's clear that there are no free forms on a surface, but a priori it would have been possible to have something in this last component t prime. But as I'm saying, this is not true. Okay, so this is fun to play around with. There are a few nice papers on that topic. Okay. More questions with which I could fill the empty space I have here? No. Okay.
I guess it looked like Josh had a question.
Yeah, please do. As I'm saying, I can't see the chat. I can
sorry,
only
did I? No?
Yeah, I did. I mean, it's kind of off a little bit, but you mentioned that there's like work in the direction of like an analog of Hop Rhino for these.
Yeah.
Yeah, like is there much work done with like harmonic maps, like the harmonic map equation in this setting?
So the first thing is that by good choice of good examples, one proves that in general, factorial torsion is not complete. Okay. And knowing or finding good conditions when it would be complete, this is unknown, completely open. Now, your question was more aiming in a different direction, right? Like harmonic map equations. Now, so there are a few people who have started looking at the question, but the problem is the ambiguity in the connection. So at the moment, I'm telling you how you can add some torsion, but obviously you don't want to add any freeform. We will have to say later what is a reasonable freeform to add, which I haven't done so far, right? I mean, any freeform an arbitrary freeform will not contain anything interesting. So how to select a good connection? Well, a good connection with torsion is always given in situation, or it's not equivalent, will exist when you have some additional geometry. So just having a Riemannian metric is not enough. See, if you have the Riemannian metric and let's say you have flow equations or other things, then you just deal with the metric and that's it. And then you take Levi-Civita connection. It's unique. It's the connection to choose when you have no other geometry than the metric. So in order to have reasonable questions about harmonic maps, you have to sort of fix the geometry. Okay. And it has to be a geometry which is adapted to the type of torsion, be it vectorial or skew symmetric or this additional part. So there's more in the setup needed than just let's write down the harmonic map equation and then just do it. But the question does make sense, right? Once this is answered, and again, I would say this is at the beginning of what's going to happen. Okay. If you look at this equation as I stated it here, then you see one thing to do further, namely to take a subgroup G inside SON. So if you know that your manifold has more structure than just the Riemannian metric, then you go on and decompose these representations further under the smaller group. And then you will get interesting things, because then this Cartan component will decompose and then you will be able to identify it with torsion, with tensor fields, and then you get interesting geometry. This has been started. It gets quickly complicated. That's the trouble with all that. But for example, in dimension 7, Stefan Ivanov and Rob Bryant have tried something like that for G2 manifolds, which looks promising. It's just, okay, a further continuation. Okay, so maybe this is enough digression. Okay, so I would like now to go to holonomy as being a basic concept for what we're doing. So I take a path gamma, and in fact now here it's already drawn to be closed, any connection nabla, and I consider parallel transport P gamma going from one tangent space to the next. Now this is the unique map such that the parallel transported vector field is going to be, well, parallel, meaning that this derivative is zero. Okay, that's just definition. Now let's have a look at closed loops for a point and null homotopic loops for a point. Then we get the restricted or reduced holonomy group of the connection as being all possible parallel transports from a point coming back to the point for all possible paths. Okay. Okay, and I take them null homotopic because I don't want to measure the local topology. I'm just interested in geometry. Okay, if the manifold is connected under weight assumptions, all this is going to be independent of P modular conjugation. So I will drop P in the notation. So I will have the holonomy group of the connection and the reduced holonomy group. Now, all these things you know from the differential geometry courses. But if now the torsion T is non-zero, which I implicitly assume all the time, then, well, okay, you can still state this is a least subgroup of GLNR, but not necessarily closed. And we know that non-closed least subgroups are bad news. Okay, this is a pathological case. In general, it doesn't happen, but there's no theorem guaranteeing it, which is a pity. I would love to have such a theorem. We do know that this is the connected component of the identity of the full holonomy group, but not much more than that. Okay. So if we continue thinking about classical holonomy concepts, now, if I assume a priori what I said before, would the definition of holonomy group would be correct for any connection. Now I assume in addition that the connection is metric. What does it actually mean to be a metric connection? Well, it means that parallel transport is an isometry. And therefore, my connection, the holonomy group of my connection is not going to be a subgroup of GLN as I had it on the previous slide, but it's going to be a subgroup of ON, right? Because all parallel, it's a group generated by all parallel transports, and its reduced part, the component of identity, is a subgroup of SON. So from the point of view of notation, the holonomy of the Levi-Civita connection, I am going to call the Riemannian holonomy group. Now, the first observation is repeated here from what I indicated on the previous slide. The reduced holonomy group needs not to be a closely subgroup, which is surprising. And actually, when you start dealing with connections with torsion, it will happen very often to you that there are things you know you're used to from classical differential geometry, and you have to check whether the property you're thinking of is still valid in connections with torsion business. Okay, many things fail that we are very used to. It fades off with years, but at the beginning, this is a challenge. The second surprising fact is the holonomy representation, maybe I should have said, on any tangent space. Okay, the holonomy is not just a Lie group. The holonomy comes with a representation for free, namely its natural action on the tangent space. So the holonomy representation on the tangent space needs not to be irreducible, even if the manifold you started with is irreducible. So this means that de Rhams theorem just doesn't hold anymore for connections with torsion. There's no local splitting principle, which would be the obvious generalization of the Riemannian case. And so in fact, what we have a larger variety of holonomy groups. And in particular, we have a larger variety of holonomy representations which occur. But this flexibility comes with a price, and the price is that you cannot classify it anymore. Okay, because in particular, this second point tells you that you cannot restrict your attention to irreducible manifolds or irreducible representations. It's just not true. You have to take into account reducible representations. So how to deal with it? Okay. So we know that curvature and holonomy go along in a very deep way. For example, we have the famous Ambrosinger Theorem from 1953, which tells us that holonomy can be computed for curvature. And how is that? Well, for any connection nabla on my manifold, I look at the Lie algebra of the holonomy group. And this is exactly the subalgebra of the orthogonal Lie group generated by the elements. So I take the curvature transformation on, take two vector fields VW. I look at the curvature transformation. I let it act on V and W, but not exactly. I put the parallel transport in front. So I move from one point to another via parallel transport, and then I use parallel conjugation by parallel transport to move back and forth to always stay in the point P for any path gamma. So up to conjugation, basically the composition of parallel transport will generate the curvature tensor. Or the curvature tensors will generate the holonomy algebra. Maybe this is the better way to put it. Okay, this is a very nice theorem. It's true for any metric connection. But if you try to put it into to work, then you realize things you used to don't hold anymore. And let me give you an example. Let's have a look at the Bianchi identities. Bianchi identities are our main tool. And unfortunately, the Bianchi identities look different for connections with torsion. So here are a few examples. If you have a metric connection, which is described by some vector field V, okay, so vector field V factorial torsion coming from a vector field V, then the cyclic sum, this sigma is my symbol for cyclic sum. The cyclic sum of all curvature transformations R, X, Y, Z is not zero, but it's rather given by the following quantity. You take the vector field, turn it into a one form, then you take the differential, this is a two form, evaluate this two form on X and Y, multiply with the vector field Z to get a vector field, and then again take the cyclic permutation of these. And this is in general not zero. Okay, so we get the first Bianchi identity for a metric connection coming from a vector field, which incorporates that vector field. Similarly, you can compute the Bianchi identity for a metric connection, which is now has a torsion being a free form, so with skew symmetric torsion. Then again, you will look at this cyclic sum of Rxy and plus I take the scalar product with an additional vector field V, because that makes it easier to write down, because this is going to be a four-form part, which is the differential of t, dt, evaluated at exactly the same vector fields x, y, z, v, minus an algebraic term. Now, this algebraic term is extremely interesting. We define a new four-form sigma t out of the torsion tensor T in the following way. T is given by the inner product of EI with T, right? Where the EIs are just an orthonormal frame. And then I take the square of this form. Now, this element here is a two form. So the wedge with itself in general is non-zero. All in all, I get a four form, and I sum over my orthonormal frame. And the first thing to check is that this sigma t is independent of the choice of orthonormal frame. There is, in fact, the second definition, but it's not so easy to grasp immediately, which does not use an orthonormal frame. But this is a very nice way. So it is a four form, which is algebraically given or algebraically induced from T, but it's not linear in T because T appears twice. Okay, so it's not a tensorial construction, but useful nevertheless. So this four form, which is going to reappear, it pops up over and over again. You see it for the first time in this Bianchi identity, plus the connection nabla, take the derivative of the torsion with respect to the connection it defines in direction V, and then evaluate it at X, Y, and Z. Okay, this gives you a first impression about how working with connections with torsion can turn out. For example, this implies that from an algebraic point of view, the space of curvature tensors looks very different from what it is in the Riemannian situation. Okay, so this maybe we keep as a first conclusion. Space of algebraic curvature tensors looks different from the Riemannian case, right? Remember that we define in Riemannian geometry the space of algebraic curvature tensors, and it's just not the same. And for example, you find that the Ricci tensor of a connection, the Ricci tensor of a connection with torsion, just defined in the usual way, is not necessarily symmetric. Okay, so one has to be careful. And that's clear because you use these precisely the properties of the space of algebraic curvature tensors to prove that the Ricci tensor is symmetric. Okay, so things start to happen here. And now let's have a look at one, and the most important theorem on holonomy, namely Berger's holonomy theorem. Given a non-symmetric Riemannian manifold MG, and fixing for the moment being the Levi-Civita connection analogy, the possible holonomy group. Okay, and I should have added irreducible. Okay, so the possible holonomy groups are either the generic case, namely the full orthogonal group S1, or one out of a list which is rather short. The groups so first all these groups correspond to certain dimension situations, so and then each of them has a particular name. So the group SPn times SP1, for example, corresponds to what is known as Quaternary manifolds, and Quaternary manifolds actually occur only in dimensions divisible by 4. Quaternary manifolds have enormous complex structure. It's not parallel with respect to the Levi-Civita connection in general. And these manifolds, for example, are always Einstein. We have Kähler manifolds corresponding to holonomy UN in even dimension. In particular, the two form defining the Kähler structure is parallel for the Levi-Civita. Then we have the even more special case of Calabi-Yau manifolds with Riemannian holonomy SUN. And not only that, this is a Kähler manifold, but it's Ricci flat. We have the case of Hyperkala manifolds, which in some sense is the cousin, or yeah, it's a cousin, it corresponds to quaternionic Kähler just as Calabi-Yau corresponds to Kähler, meaning you have the holonomy group SPN, again a parallel two form, and it's Ricci flat. We have what is called parallel G2 manifolds with with a parallel free form. This free form generates the G2 structure, and they are also Ricci flat. And we have the situation of parallel spin 7 manifolds. So the group is spin 7, and we have a parallel 4 form, and it's again Ricci flat. What else we can observe is that here we have, so Calabi-Yau and Hyperkala, we have even dimensions again. And we have G2 only in an exceptional dimension 7 and spin 7 only in exceptional dimension 8. So in this sense, we have a difference, right, which happens here because the other 4 appear in families, whereas these 2 are single children, so to say, right? Because they don't appear in families, they just appear in isolated dimensions. On the other side, we have common properties by curvature. So if we look at curvature, the division line would be more about those who are Ricci flat and those who aren't. And then again, I can still look from a different point of view, namely from the point of view of dimension, and not looking at families, I see all of these occur in even dimension, except for the G2 case. This is the only odd dimensional situation, right? And so it shows already that there must be something very special going on in dimension 7. Now, I'm not going to say anything about the long story about construction of Calabi-Yau manifolds, Hyperkala, parallel G2 spin 7. We know all from Calabi to Yau to Joyce, etc. We know that this theorem of Berger was not so much a classification theorem, but it was a list of possibilities. And actually filling this classification with compact examples was a work program for differential geometers for decades. Okay. So, but by now we know that all these have non-trivial compact examples. But even with that information, we see that maybe except for the 2 cases here, quaternionic Kähler and Kähler manifolds, all the other manifolds are not manifolds you are going to encounter in daily life if you are not looking for them, or if you're not working in the area. Most manifolds are not covered by this theorem, right? So either the holonomy is general, SON, but then it doesn't contain any information. It just tells you it's a generic metric period. So what about interesting manifolds having interesting additional geometric structure, but which are not of any of the types listed in here? Most manifolds are not covered by the theorem. Can we say anything about them which would be useful from the point of view of holonomy? Question 1. Question 2. Okay, so I kept saying that this cannot be generalized, or this is not in an obvious way possible in situations for connections with torsion, because, for example, I cannot restrict my attention to irreducible representations, because in general, I will have reducible holonomy representations on irreducible manifolds. So if I cannot expect getting a list of the type I described here, is there anything else I can say qualitatively about the holonomy? So what would be a good reformulation or a good replacement of this theorem for connections with torsion? And in fact, next week, I'm going to present the generalization and how to use it and where it comes from. Basically, one has to change the point of view of this theorem. As it looks now, this is what I would call a list theorem, right? Because it gives you a finite list. If you have the following situation, then you are in one of the following cases, 1, 2, 3, 4, etc. So we have to give up this list picture and look at it differently. You can think about what would be a different look at this table, by the way. It's not terribly difficult. Maybe you will find. This is where mathematical creativity comes into the play. Okay, so these are the questions we want to answer or that we want to use as a guiding line for what's going on. Second main theorem on holonomy that is useful is the general holonomy principle. This is totally different in kind because the Berger theorem said something about Riemannian geometry and only Levi-Civita connection and only irreducible manifolds, etc. Now this is almost metaphysical, I would say. So given a manifold, a real complex vector bundle over M with any connection number, then the following conditions are equivalent. First is, my vector bundle has a global section alpha, which is invariant under parallel transport. Meaning, whenever I have a path gamma between 2 points P and Q, I can compute my section alpha at the point Q by just taking alpha at the point P and parallel transporting it by P gamma. And I'm not saying anything about the path because this is right for any path. Second equivalent formulation, this vector bundle E has a parallel global section alpha. Parallel just meaning nabla alpha equal to 0. And third variation, in some point P, there exists an algebraic vector alpha naught in the fiber EP, which is invariant under the holonomy representation on this fiber, because I started with a connection. So this connection acting on this vector bundle induces holonomy representation on fibers. Okay. In particular, I have the following easy, very easy corollary, but crucial for many applications. If you want to count the number of parallel global sections of a vector bundle, this corresponds to the number of trivial representations in the holonomy representation on the fibers. Now, do I have an empty slide here? No, I don't. In particular, if we look back at the Riemannian case, okay, in the Riemannian case, I had said that the building blocks correspond to holonomy representation acts on the tangent space by an irreducible representation. Now, if it acts by an irreducible representation, and the manifold is not a curve, which is not the case I'm interested in, it means in particular that there are no trivial representations. Okay. So the situation of this corollary usually does not happen in the Riemannian situation. But if we now have torsion, then we are going to have parallel global sections, and these parallel global sections will actually, so they will in general exist, parallel tensor fields, spinor fields, or whatever parallel objects, okay, with respect to the connection nabla. So this is not a theorem. There always exists a parallel object. Just saying that is the typical situation will be that they are parallel objects with respect to the connection nabla. And so these parallel objects with respect to this connection nabla, they describe the geometry. Okay. Now, just as if we go back here, we have this situation here that we do have a parallel object. So how is that compatible with what I said before? Well, these objects are tensors, but they're not, so that the holonomy representation is irreducible on the tangent space, but it's not irreducible on the tensor spaces, right? So the space of two forms will contain a trivial representation because, I mean, UN on two forms has indeed one trivial representation. And similarly, on the space of three forms, there will be one trivial representation, and on the space of four forms, there will also be one. Okay, so in higher tensor bundles, I can find invariants, but not on the tangent space. Whereas here in this situation, I may already encounter parallel vector fields. Completely new situation if we compare it to Riemannian case. Okay, so the general holonomy principle is the same, of course, in all situations, but in practice, it differs. I brought you a slide from my differential geometry course. Okay, I just decided not to delete it. So we can give the question whether manifold is orientable a holonomy point of view. Normally, we don't think of orientability as being a holonomy property. For the following reason, if we look at the space of n forms on Rn, then the determinant is an element. It's a multilinear antisymmetric element, of course, in n variables. The determinant is SON invariant, but it's not, oops, macro not working. I have a new computer. It's SON invariant, but it's not ON invariant. Okay, so the determinant is, I mean, in this top line bundle, just the invariant measuring non-triviality. Therefore, we have, by the general holonomy principle, the nice corollary. A manifold is orientable if and only if the full holonomy group, not the reduced one, is inside SON for any metric connection nabla. And if this is the case, the volume form is going to be nabla parallel automatically because the volume form is just the manifold version of the determinant. And the proof is one line. So the volume form is basically the determinant. I take E1, wedge E2, wedge En in some point. And then I apply the holonomy principle to this, saying that a parallel object will correspond to a holonomy invariant object. Okay, and well, it just means, I mean, if we all know this example, right, of a orthonormal frame, which is parallel transported along the middle line of a Möbius strip, right? And we should see that it measures non-trivial, this determinant as a non-trivial element of holonomy. And this is just, of course, the orientation reversal. Okay, good. Shall I say something more here, questions? Or shall we have still one or two slides about trying to get to the homogeneous situation? Jeff, who is not sleeping?
I think probably we can go to the homogeneous case. Yeah.
Okay, good. I mean, we started a few minutes late, so let me just refill my pot of tea. Where is it? Now, the Ambrosinger Homogeneity Theorem is the first step towards saying why connections with torsion occur in a natural way in differential geometry. So, the version of the theorem I present here is the following. Assume you have a complete Riemannian manifold MG equipped with what is called a homogeneous structure. So by definition, a homogeneous structure is a metric connection nabla with some torsion T and curvature R such that the curvature and the torsion are parallel. So this is the first defining condition. Okay, where did it go? Curvature and torsion parallel. And this, whenever this happens, even only if, then this is going to be locally isometric to a Riemannian homogeneous space, just in the usual sense. So we can detect a transitive group action by a connection property. I mean, this I find just totally crazy, right? Because if we look at it from this point of view, this is a system of non-linear differential equations, whereas this has nothing to do with differential equations. It's just a question of the existence of a group action. So the theorem says these two are equivalent. Now let's have a look at the situation of symmetric spaces. A symmetric space in this approach would correspond to the situation of vanishing torsion, so what I would call the integrable case. And then these two equations, now if T is 0, then the second equation is trivial. And the first equation says that the curvature tensor is parallel for the Levi-Civita connection. And this is something we know. One possible approach to symmetric spaces is that these are manifolds where the Riemannian curvature tensor is parallel for the Levi-Civita connection. So if you ever asked yourself how to generalize that to non-symmetric homogeneous spaces, this theorem is the answer. Okay. Now, intuitively, the reason is, I mean, the other approach to symmetric spaces is via certain reflections, point reflections in a point, which should be isometries and something. And now if one has this local reflection property, which defines symmetric spaces geometrically, then you can use it to prove that this had actually to be a 5-0 tensor with a certain antisymmetry property. And then you realize algebraically that the only algebraic tensor which would satisfy this antisymmetry property is a 0 tensor, and therefore it's 0. That's how the two are related approximately. Okay. But so we see existence of connections with good properties satisfying certain equations measures whether my manifold is homogeneous. Obvious question, is this connection unique? And the answer is yes, in a non-trivial way. So first, if I have such a connection, nabla, then this will be called an Ambrosinger connection. Okay, so any connection fulfilling the properties of the theorem, meaning these two equations, will be called an Ambrosinger connection. So Ambrosinger connection is on a given manifold normally unique. This will be a non-trivial consequence of what we do next week. And this is true except on spheres, Lie groups, and everything which is covered by them, which should not surprise us, because on Lie groups, we had seen this family of connections nabla S. So in that sense, it was not unique. Right? So the case of Lie groups was exceptional in the sense that we have had something flat, and here also it appears as being exceptional because there's more than one connection which satisfies these two properties, which one has to check. Okay, now we take our machinery. And the first machinery that we can put into it is that we have this Cartan approach to types of torsion, namely decompose the type of tensors into the three components. And therefore, we obtain in a natural way that with a Riemannian metric, of course, there exist three classes of homogeneous spaces which just correspond to the Cartan type of the Ambrosinger connection. Right, so we have those with Factorial Torsion, we have homogeneous spaces with Skew Torsion, and then we have homogeneous spaces with this, well, non-interpretable type of torsion. So one answer why connections with torsion are important and interesting is they give us a natural classification scheme for homogeneous spaces. As a matter of fact, again, examples to follow later, it turns out that if you look at these two equations, okay, even for a non-Riemannian and non-homogeneous manifold, you have basically two equations. So you can weaken the system by either throwing away one equation or modifying the equations. And it turns out that actually what you throw away is the curvature condition and you keep the torsion condition. Okay, so the empirical observation is that for non-homogeneous manifolds, metric connections with parallel torsion are going to be the instrument of choice and will be natural and useful.
Okay, can I ask us some questions?
Sure, all questions you want.
Does it, I guess, does it follow with this nabla R is 0 and nabla T is 0, does it imply that T is also closed or maybe not?
No. I will have more comments next week about what, do I have an empty slide here somewhere? Just a second, not this one, but here, yes. So we have these two conditions which we want to compare, namely nabla T equals 0 versus the equation dt equals 0. And these two are totally different.
Even with like the homogeneous like structure, even with nabla R is 0, it's still different?
Very different.
Okay.
Almost never compatible. So what do I mean by that? Well, if nabla T is 0, then you conclude that dt is equal to twice this element sigma T I defined before. So if you have parallel torsion, then in order to have closed torsion, you need sigma T to be 0. Okay. When is sigma T equal to 0? And then you have two cases to consider. One is your manifold is of dimension 4. Then you are lucky because then you realize that algebraically, for any free form in dimension 4, this form sigma T is automatically 0. Sigma T is 0, whatever is T. And therefore, it's going to be closed automatically. So in dimension 4, the two are basically equivalent, right? And if four-dimensional geometry is what you want to do, wonderful. If it's not the case, then you're in big trouble. Because sigma T equals 0 is a case. Okay, degenerate in the sense that if you state the theorem nicely, like suppose you have nabla T equal to 0 and sigma T equal to 0, then basically it's a Lie group. With a few more assumptions, and I will state the theorem next week.
And I guess is the uniqueness maybe recovered? So suppose you further assume that T is closed. Is the uniqueness just recovered by the cohomology class of T maybe?
Uniqueness of what?
of the homogeneous structure.
No.
Hmm.
No, because this is a local property. So,
Oh, I see.
no. dt equal to 0 is a bad condition from the point of view of differential geometry and of this theorem. Okay. Now, of course, you can construct examples where T is closed. In particular, if you're happy with Lie groups or dimension 4, then that's the way to go. If you don't want these, and you go, say, to other families of geometries, then experimentally you will see that T will never be closed. So, for example, I actually have the slides still with me, but maybe I just say it like here. If you have a nearly Kähler manifold, okay, then the dimension n is 6, then look at sigma t. Sigma t is a 4 form. My manifold has dimension 6. So if I dualize via Hodge operator my 4 form, oops, wait, okay. So I take Hodge dual of sigma t, this is a 2 form. You can ask yourself, what 2 form do you get? Well, actually, you get the Kähler form. And the Kähler form, as we know, is really a non-degenerate 2 form. So in that sense, you see, I mean, and basically, the formula is not as nice anymore, but basically the same happens for other almost Hermitian manifolds. Sigma t carries information about the geometry. And for the geometry to be non-trivial, sigma t will be non-zero.
Mm-hmm.
Right? Same in dimension 7 for a nearly parallel G2. There again, the formulas are always qualitatively of the same way. It's just that the nearly parallel G2 is particularly beautiful. Then this Hodge star is going to be a free form, and it's then just the free form defining the G2 structure. And again, we know that the free form defining a G structure is really as non-degenerate as a free form can be. So, and the form is 0 if and only if the Hodge star is 0. So this is not only not 0, it's far from being 0. So that's why these conditions, it's something I haven't resolved so far, right? Coming from homogeneous manifolds and the examples that we treat, imposing delta t equal to 0 is a completely non-intuitive and non-natural condition. But I know that in other areas, this is what one would like to look at. So I don't see the final answer.
Sure.
Yeah. Okay, I have prepared a few slides about the nearly Kähler case, but I'm not sure whether I should do that or we should stop here and continue next week. You decide.
Maybe could we just go back to the homogeneity theorem slide?
Yeah, sure.
Maybe I think I had another question, or no, maybe not this one. Which slide was it? I think one more, maybe back. Oh no.
Okay.
Right. Yeah. So this uniqueness question. So unique except for spheres, Lie groups, and their coverings.
Yeah. So in particular, also not for projective spaces. Right. But except the reason being, so Lie groups are special because they correspond to the flat case, and spheres are special because they correspond. So if you look at the symmetric case, the sphere is just the standard, the holonomy representation is just the standard representation of SON on Rn. Okay. And so one needs to take these two extreme cases apart, right? Spheres would be like the generic holonomy, and Lie group is basically no holonomy at all because it's flat. So everything except the two degenerate ends of the picture, anything in between will be unique. Right? And I mean, yeah, this is just what the equations are, right? Now,
maybe, sorry, can I just ask one more time? I'm not sure I understand the statement. I mean, is the connection unique? I mean, because somehow the Levi-Civita connection on the round sphere and then the sort of Cartan connection on the 3-sphere.
Yes, but I changed the group action. Homogeneous space with respect to a certain group action.
Yeah. Oh, okay. Oh, okay. All right. Yeah, that makes sense. Basically.
So the connection depends on the group action. So in the situation where you have, and this is really a subtle point here, where you have different groups acting transitively on the same manifold, you will get different connections because they correspond to a different group. And the connection will be invariant under this action.
Okay, yeah.
Right? But in fact, the metric is going to change because, I mean, the round metric, so the sphere can be written as the round metric or as a Berger sphere, for example.
Right.
Okay, but the metric induced for the Berger sphere is not the round metric induced as a symmetric space. So the metric really changes in these pictures, and the G2 metric on the 7th sphere is again not the round metric. So it's a very, and classifying these invariant metrics is okay, and furthermore spheres are not allowed. That's also,
Sure.
well, I had to exclude spheres. So speaking about spheres is wrong anyway.
But in the end, the statement is a theorem. The statement is, I mean, the Riemannian metric is fixed. You have a metric with some connection, some special connection, and then you.
Right. So if you fix the metric, then there's going to be only one connection except for spheres on Lie groups.
Yeah. Okay, yeah.
It's a funny theorem. I agree with that. So now let me just add a few sentences about the classification we get. Right, I said that now I take the Ambrosinger connection, and so I will get 3 classes of homogeneous spaces depending on the algebraic properties of the torsion of that connection. And so let's have a look. What is the class of homogeneous spaces which corresponds to skew torsion? Skew Ambrosinger torsion. So this is what is known as the class of naturally reductive homogeneous spaces. The traditional approach or the traditional definition of naturally reductive homogeneous spaces is that this is a homogeneous space with a metric of a certain type. Namely, it's naturally reductive if, so I take M equals G over H, if the Lie algebra H admits a reductive complement script M inside the big Lie algebra G, such that the following property holds for the metric. So we know that the Riemannian metric on the homogeneous space induces an inner product on script M. And this inner product on script M should satisfy for all Lie algebra elements X, Y, Z, which of course correspond to vector fields on my manifold. I take the commutator XY, I project it down to script M, which is reasonable because my Lie algebra G is decomposed in H plus M, right? So I project down to M, take the inner product with Z, plus, now the other way around, I take XZ, project to M, inner product with Y. This should be 0. Observe how this is the generalization to a homogeneous space of the corresponding equation we had for Lie groups, for the metric to be B invariant. So naturally reductive homogeneous space generalizes B invariant metrics And general theory of principal fiber bundles gives you a metric, a connection, sorry, because I have the natural projection, which is in fact a Riemannian submersion from G to G over H. And this makes the Lie group G into an H principal fiber bundle over G over H. And this description of a fiber bundle gives me for free a metric connection with torsion. And if you do the computation, you find that the torsion is going to be commutator XY projected down to M again in a product with Z. So just XY Z, yes, this is just what's written here. Okay, so the torsion is just the first summoned in this property of the metric which defines naturally reductive manifolds. And so this connection by the general holonomy principle will satisfy that its torsion and curvature are parallel. So this is just the Ambrosinger connection from the theorem. Okay, so, and furthermore, we see that the condition for the metric to be naturally reductive is just equivalent to T is a freeform, right? So we see that naturally reductive homogeneous spaces by this Ambrosinger approach correspond to one algebraic type of torsion. So I repeat it actually down here. The condition star just means T is a freeform. So we have one of the three types of homogeneous spaces here. And we see also that if G over H is symmetric, symmetric just means, or well, symmetric in particular, and all groups being connected, where it means that the commutator M with M is inside H. But if that's true, then I see that these commutator parts which appear here are going to be 0 in the symmetric space case. And therefore, the torsion is going to be 0 whenever M times M lies in H, because then there's no M projection. And then the connection just boils down to the Levi-Civita connection. And so again, we see not only qualitatively, if I put T equals 0 in the theorem, I recover the symmetric case, but even in this more detailed description of naturally reductive spaces, I see how symmetric spaces are the trivial case with vanishing torsion. And naturally reductive homogeneous spaces will just be our playground of connections with skew torsion. By this Ambrosinger theorem, this is the most natural thing to do. And if you want to classify these spaces, then connections with torsion are just the right tool to use. Okay, and now I think we should definitely stop. Thank you very all for not falling asleep.
Yeah, thank you. Any more questions? Okay, well, yeah, thank you. I'm gonna stop the